Locality means that to get from one point to another, you somehow have to make a connection in space between these points. You cannot suddenly disappear and reappear elsewhere. At least that was Einstein's idea. In quantum mechanics, it's more difficult. Just exactly how quantum mechanics is and is not local, that's what we will talk about today. To illustrate why it's complicated, let me remind you of an experiment that we already talked about in a previous video. Suppose you have a particle with total spin 0. The spin is conserved and the particle decays into new particles. One goes left, one goes right. But you know that the two new particles cannot each have spin 0. Each can only have a spin with an absolute value of 1. The easiest way to think of this spin is as a little arrow. Since the total spin is 0, these two spin arrows of the particles have to point in opposite directions. You do not know just which direction either of the arrows points, but you do know that they have to add to 0. Physicists then say that the two particles are entangled. The question is now what happens if you measure one of the particles' spins. This experiment was originally proposed as a thought experiment by Einstein, Podolsky and Rosen, and it is therefore also known as the EPR experiment. Well, actually, the original idea was somewhat more complicated, and this is a simpler version that was later proposed by Bohr, but the distinction really doesn't matter for us. The EPR experiment has meanwhile actually been done many times, so we know what the outcome is. And the outcome is that if you measure the spin of the particle on one side, then the spin of the particle on the other side has the opposite direction. Okay, I see you are not surprised, because we knew this already, right? So what is the big deal? Indeed, at first sight, entanglement does not appear particularly remarkable because it seems that you can do the same thing without quantum anything. Suppose you take a pair of shoes and put them in separate boxes. You don't know which box contains the left shoe and which the right shoe. You send one box to your friend overseas. The moment the friend opens their box, she will instantaneously know what's in your box. That seems to be very similar to the two particles with total spin 0. But it is not, and here's why. Shoes do not have quantum properties, so the question which box contained the left shoe and which the right shoe was decided already when you packed them. The one box travels entirely locally to your friend, while the other one stays with you. When she opens the box, nothing happens with your box, except that now she knows what's in it. That's indeed rather unsurprising. The surprising bit is that in quantum mechanics this explanation does not work. If you assume that the spin of the particle that goes left was already decided when the original particle decayed, then this does not fit with the observations. The way that you can show this is to not measure the spin in the same direction on both sides, but to measure them in two different directions. In quantum mechanics, the spin in two orthogonal directions has the same type of mutual uncertainty as the position and momentum. So, if you measure the spin in one direction, then you do not know what's with the orthogonal direction. This means if you on the left side measure the spin in up-down direction and on the right side measure in a horizontal direction, then there is no correlation between the measurements. If you measure them in the same direction, then the measurements are maximally correlated. Where quantum mechanics becomes important is for what happens in between, if you dial the difference in directions of the measurements from orthogonal to parallel. For this case, you can calculate how strongly correlated the measurement outcomes are if the spins had been determined already at the time the original particle decayed. This correlation has an upper bound, which is known as Bell's inequality. But, and here is the important point, many experiments have shown that this bound can be violated, and this creates the key conundrum of quantum mechanics. If the outcome of the measurement had been determined at the time that the entangled state was created, then you cannot explain the observed correlations. So it cannot work the same way as the boxes with shoes. But if the spins were not already determined before the measurement, then they suddenly become determined on both sides the moment you measure at least one of them, and that appears to be non-local. So this is why quantum mechanics is said to be non-local, because you have these correlations between separated particles that are stronger than they could possibly be if the state had been determined before measurement. Quantum mechanics, it seems, forces you to give up on determinism and locality. It is fundamentally unpredictable and non-local. Okay, you may say, cool, then let us build a transmitter, forget our frequent flyer cards and travel non-locally from here on. Unfortunately, that does not work, because while quantum mechanics somehow seems to be non-local with these strong correlations, there's nothing that actually observably travels non-locally. You cannot use these correlations to send information of any kind from one side of the experiment to the other side. That's because on neither side do you actually know what the outcome of these measurements will be if you choose a particular setting. You only know the probability distribution. The only way you can send information is from the place where the particle decayed to the detectors, and that is local in the normal way. So oddly enough, quantum mechanics is entirely local in the common meaning of the word. When physicists say that it is non-local, they mean that particles which have a common origin but then were separated can be stronger correlated than particles without quantum properties could ever be. I know this sounds somewhat lame, but that's what quantum non-locality really means. Having said this, let me add a word of caution. The conclusion that it is not possible to explain the observations by assuming the spins were already determined at the moment the original particle decays requires the assumption that this decay is independent of the settings of the detectors. This assumption is known as statistical independence. If it is violated, it is very well possible to explain the observations locally and deterministically. This option is known as superdeterminism, and I will tell you more about this some other time. That's it for today. Thank you for watching. See you next week.